So our topic for today is Kähler manifolds. So we've been talking last week about almost complex structures, symplectic structures, how they relate to each other. And one of the things we proved, this is essentially just kind of a linear algebra result, that if I have a manifold M, I have an almost complex structure, which I'll just remind you is a map of bundles from the tangent space, the tangent bundle to itself, such that J squared is minus the identity. And that exists if and only if there's an almost symplectic structure, which is a two form, which is non-degenerate, but maybe not closed. So I'm going to put question mark over whether it's equal to 0, because it could be equal to 0, but it doesn't have to be. That's almost assuming that it's closed. All right. So you can sort of ask, well, what kind of combinations of these things can you have, right? So there are kind of niceness properties we want for complex structures and for symplectic structures. So we can ask, is this form closed? So is the almost symplectic structure honestly symplectic? And we can ask, is J integrable? So is the almost complex structure genuinely complex? And these are both kind of flatness conditions. But I'm not going to ask that the metric is flat, because flat metrics aren't interesting enough. All right, so if the answer to both is no, it's just an almost complex manifold. You could also say almost symplectic, but people tend to say almost complex instead. If you say yes, it's a complex manifold. If you to the integrability, it's a complex manifold. If you say yes to d omega equals 0, it's a symplectic manifold. And if both those things are true, if the complex structure is integrable and the compatible symplectic form is also honestly a symplectic form, it's closed, then we call this Kähler. That's interesting. So a Kähler manifold is a manifold that has a complex structure, a symplectic structure, and they're compatible with each other in the sense that we discussed before, which exactly means that if I take the symplectic structure, I apply it to a vector, I apply it to J times another vector, that gets me a metric. And so different people will kind of emphasize different aspects of this. Some people will emphasize the metric and say this metric is a Kähler metric. But what that means is when you use this same formula to define omega, you get a two form that's closed. So this is kind of the nicest possible situation you can have with a metric, a complex structure, a symplectic structure, all compatible with each other. And these play a really important role in differential geometry because their differential geometry is so nice. A metric that has this property is a very good metric. It sort of plays very well with the complex structure. All right. So as I say, some people will kind of emphasize the existence of the complex and the symplectic structures. Some people will emphasize the metric. Now, what does this look like when we actually write things out in coordinates? So I'm going to take omega. Omega is a real valued two form, but I can think of it as a complex valued two form with 0 imaginary part. And I can expand it using this expansion we had before. So I choose a complex set of coordinates around a point on my manifold. And all of my two forms are a sum of terms like dz wedge dzi wedge dzj. So that's a 2-0 form. Dzi wedge dzj, dzi wedge dzj bar, that's a 1-1 form. And dzi I bar wedge dzj bar, that's a 0, 2 form. All right, and I have functions in front of these. I didn't explicitly put that all of these are functions smoothly depending on the coordinates z1 up through zn, but that's what's happening. All right, so if I'm going to have compatibility between the symplectic structure and the complex structure, I have to have that multiplication by the complex structure is a symplectomorphism. It preserves the symplectic form. So if you think about that for a minute, that will actually tell you that you can't have any contribution from the 2, 0 form, and you can't have any contribution from the 0, 2 form. And the reason is, so this J star, that just means look at the 2 form W, J, U, W, J, V. So that's supposed to be the same as W. But if I put in 2 eigenvalues that both have eigenvalue I, I'm going to multiply my form by I times I, which is -1, and it's no good. It's not the same. If I put in 2 with eigenvalue minus I and minus I, again, I'm not going to preserve my form. It's not going to work. I'm going to get also going to multiply by -1. So the only way I can get something that respects the complex structure is if I only have contributions from the 1, 1 form. So omega has to be a 1, 1 form in order for this, for it to be Kähler. And for kind of normalization reasons, I had put these functions bij in there, and I want to multiply that by -2 times I. We'll see in a moment why people kind of prefer that. And I can rewrite my form in terms of these h's. So I'm just going to remind you what's happened here is I've thought of the complex structure as fixed, and I've thought about, oh, what would a compatible symplectic form look like? And actually I haven't used anything about being a symplectic form yet. This would be true for compatible almost symplectic form as well. It has to be a 1, 1 form for one thing. The other thing is, well, it's real, right? I started with an actual 2 form with real coefficients, and then I thought of it as complex in a boring way. So it's equal to its own complex conjugate. And I just want to emphasize here, when I'm taking the complex conjugate of a complex form here, all I'm doing is complex conjugation on like the coefficient. So it's sort of a trivial operation on the underlying forms. It's just, I think of it as a real valued form plus I times a real valued form, and I send it to minus I times that real valued form. All right. So if I take the complex conjugate of omega, well, I get this expression, the I over 2 becomes a minus I over 2. This hij gets conjugated. My dzi turns into a dzi bar. My dzj bar turns into a dzj. And then I want to swap the order of my wedges. So I pick up an extra minus sign from swapping the order of the wedges. I get I over 2 h ji bar dzi wedge dzj bar. All right. So I get out of this, in order to have omega be a real form, I have to have that these hij's form a Hermitian matrix. So that's kind of why I snuck that I into there. I would rather think about this Hermitian matrix rather than the skew Hermitian matrix that was given by the original bij's. All right, so when I sort of take my 2 form and I write it in coordinates this way, I get a Hermitian matrix at every point in my coordinate chart. And it's useful to think about what is the metric G in terms of this matrix, right? So to compute the metric G, what's going to happen? Well, because I'm putting in a 1-1 form, oops, G of, if I put in 2 DZIs is equal to 0, and similarly, if I put in 2 I bar and DZJ bar, both of these are 0. They don't contribute at all to the metric. So kind of the only interesting thing to compute is this guy. And I get 1/2 Hij is the pairing between these vectors. So kind of another reason to think about, why would I throw in that weird factor of I? It's, well, when I try to write out the matrix of the metric instead of the matrix of the symplectic form, there's naturally an I that shows up in there because the metric and the symplectic form are related by this equation. So that multiplying by the complex structure multiplies me by I or minus I. So sort of extra factor of I shows up. And you can actually check that the Hermitian form you get comes, it ends up reducing to complex dot product with this Hermitian matrix H in the middle. So I'll probably leave to you kind of the details of sorting that out. But the kind of important thing I'm getting out of this is that I can write my metric, which remember is a real valued symmetric bilinear form, which is positive definite, as the real part of complex dot product with this H in the middle. So the other reason people think about this guy H is it's actually naturally kind of the metric that describes, sorry, it's the matrix that describes the metric, which a lot of people think is as kind of the natural thing to look at in the Kähler form. And that half comes from the fact that there are like 2 real coordinates corresponding to every complex coordinate. So in particular, I get an extra condition on my H. If I'm going to have compatibility between my complex structure and my symplectic form, this Hermitian matrix has to be positive definite. So let me just remind you, right, the 2 things I need for a symplectic structure to be compatible with a symplectic form. One way of saying it is that omega of uv is equal to omega of ju jv, so that implies that it has to be a 1-1 form. And then I have to have that this inner product is always positive. And this is expressed by this guy H being positive definite. So that's the other reason to sort of do this change to H. That if I were thinking about the skew Hermitian matrix B, I can't ask it to be positive definite, right? I don't think there's a kind of natural condition on skew Hermitian matrices so that like I times them, maybe it's minus I times them, is positive definite. There's sort of no good linear algebra way to say that. So it's better to think about this guy H that we ultimately want to be positive definite. That's kind of an extra condition on the complex structure and the symplectic form and how they play together, but there's no good way to say it without just writing out what the metric is and saying, this had better be positive definite. Any questions? So what I've told you thus far is what you would need to get an almost symplectic structure compatible with the usual complex structure on Cn. That you would need a matrix H that depends on the point such that it's Hermitian and positive definite at each point. But we also want an actual symplectic structure, so we have one more condition. We need that the exterior derivative of this is 0, and well, we could just write that as a condition. If we want to be all fancy and complex about it, we can instead ask that del bar and del of omega is 0. Those are equivalent properties because we're on an honest complex manifold. Let me just recall that because we're on an honest complex manifold, we actually do have that d is equal to del plus del bar. So if del and del bar are both 0, then the exterior derivative of 0, and if the exterior derivative is 0, then del and del bar are just components of it, so those are 0 as well. So this is kind of the picture we want to have if we have a Kähler metric.
Sorry, Ben, can I ask a question?
Yes, of course.
If we would have considered applying G to d by dyi and d by dyj, would we have wound up getting the same condition out? Like the same, it would have turned out that the same kind of positive definiteness would come out of that?
Yeah, sorry, I didn't actually write this as clearly as I should have. Right, what's going to happen here? Let me write this a little more clearly. So I can identify. So I have this usual identification of the tangent space to Cn with the real span of ddxi and ddyi, right? And when I do this, I'm going to send a complex valued vector with n components to the real part of ai times ddxi plus the imaginary part of ai times ddyi. And under sort of this translation, I'm going to match, maybe I'll give this a name. Let's call this V of AI. So I'm going to get that the metric G applied to V of A, V of B, that's a real number. And if you go through all the algebra, what you'll find is that's the real part of A star HB. And this calculation doesn't kind of go through all the details, but it's kind of the key thing you have to know.
Okay. So I mean, another part of the calculation would have been figuring out what G of ddyi, ddyj is, right? I mean, that is part of, yeah. Okay. So it's just a step you skipped. Gotcha.
Yeah. Right. Yes. And the point is, this thing is an inner product on the real vector space, Cn, if and only if H is positive definite Hermitian.
Okay.
So yeah, that's kind of the linear factor. This is an R inner product if and only if H is positive definite Hermitian. And in fact, this is sort of a useful thing to think about for the first question on homework 2, like both kind of what's going on here and what's the imaginary part of this product. That's kind of it's directly relevant to question 1 on the homework. All right, any other questions about this linear algebra stuff? And unfortunately, Canis de Silva kind of skips this part. She just sort of says, oh yeah, you have this tameness condition, and if you go through the algebra, that implies H is positive definite Hermitian. And what she means by if you go through the details, it's writing out, like, for example, this inner product. I mean, I suspect you could look directly at this calculation with dzi and dzj bar, and if you thought hard enough about how complex linear algebra works, read off this condition, this equality. But I think it might be slightly easier to actually do everything out in terms of x's and y's. But I think if you thought hard about it, I hope I didn't put the star on the wrong side, but it doesn't matter too much. All right, cool. And then, as I say, yeah, you have this last kind of closed condition. And one of the things that's kind of worth thinking about always with this stuff is, what cool little Moser type theorem do I get? So having this compatible complex structure makes this kind of Moser theorem argument much nicer. So if I have a compact complex manifold in 2 different Kähler forms, so 2 different symplectic forms that are compatible with the fixed complex structure, and which have the same class in H2, then actually the 2 manifolds are symplectomorphic. And you just use the Moser trick, right? So you take the weighted averages of these 2 symplectic forms, you look at the straight line between them in the space of symplectic forms. That's a funny looking T. It looks a lot like a Z. I was wondering why I put Z there. And all of those intermediate guys are also Kähler forms. So if I just take the same weighted average of the two Kähler metrics, I'll get another metric, and it will be the Kähler metric corresponding to the weighted average of these guys. So every step along the way is Kähler. I'm never changing the H2, so I can always integrate to, I can always find the vector field I need to make the Moser trick work. And so I can get an isotopy that relates these two symplectic forms. So kind of the important invariant of a Kähler form is just its class in H2. If you fix the complex structure, and I tell you the class in H2, there's only one Kähler form up to symplectomorphism. And you'll often hear people talk about the Kähler class. It's called the Kähler class. And I mean, I should mention, different complex manifolds can have lots of different Kähler forms. For example, you can always scale your Kähler form, but it can be more complicated than that. And I'll just mention the same argument shows that if you have two different Kähler forms, then if you take the weighted averages of them, well, you won't get symplectomorphic things. They'll have different cohomology classes, but you'll still get a straight line of Kähler forms between them. So the space of different classes in H2 that correspond to Kähler forms is convex. And since it's also closed under scaling, it's a convex cone. In many cases, it's actually nice polyhedral cone. That's not always the case. This is called the Kähler cone. And if you're wondering how you would get like inequalities defining this cone, if you have a Kähler form, then you get a volume form on every complex submanifold. So in particular, if you have a compact complex two-dimensional submanifold, a Riemann surface inside your complex manifold, then integrating the Kähler class over that, you have to get a positive number because you're finding the volume of that Riemann surface. So for every Riemann surface in your complex submanifold, you get an inequality constraining this Kähler cone. And in many good cases, that's the only inequality you need, but that's not true in every single case.
That sounds like the Neff cone. Is that?
Yeah, it's effectively the Neff cone. So I mean, the Neff cone is like by definition. I'm telling you, the Kähler cone has to lie inside the Neff cone.
Okay.
In many cases, they're the same.
Okay, right. So you're just saying there could be other constraints on the Kähler cone.
Yeah, I don't think they're always. Well, yeah, maybe for projective varieties, they actually are the same, right? I mean, the Kähler cone is effectively the ample cone.
Okay.
So it's sort of, and that is usually the same as the Neff cone. I didn't look up carefully what all the relationships between these things are, so I'm not going to kind of commit to what's the same, but in practice, quite, somehow part of this is like because I sort of in geometric representation theory, usually I'm looking at varieties where things are kind of much simpler and a lot of these kind of weird issues don't pop up. So, somehow I always worry a little bit like, okay, yes, in every variety I've ever thought about, this statement is true. That doesn't mean it's always true. There are a lot of weird, complex manifolds out there that aren't projective varieties, and I don't think very much about those. So I usually hesitate to make any statements about
I have a random question.
Mhm.
You can ignore me if it's off, if it's too far off, but you know, you can talk about the integral cohomology of a compact manifold, right? Like, is there any, what's the significance of the class of a Kähler form being an integral class? Is there any particular meaning to that?
Okay, someone says they're pretty sure there are varieties where the ample and Neff cone don't agree. Yeah, probably I like read some theorem somewhere that they are the same, but with some hypotheses, and I don't remember what the hypotheses are. But sorry, to answer your question, I mean, I think the answer is yes, but it's going to be a while before we can say anything intelligent about it. So
Okay, fair answer.
one of these things where that's a good observation to flag, but it's yeah. I mean, so it's unfortunate because I'm sure there are some people in this class who know a fair amount about, you know, projective algebraic geometry, and I can say that will not make sense to people who haven't thought about that world. One way to think about that is in algebraic geometry, you know, projective space, we're going to talk about, has a sort of fixed Kähler structure that everybody loves, right? And on a projective variety, I would say, oh, your Kähler class being integral, that's a condition you need in order for your Kähler structure to come from embedding in complex projective space with the Kähler structure that everybody expects on it. Right? And if you were an algebraic geometer, I would say, oh, and actually what that's telling you is like that Kähler form is the curvature of a connection on a line bundle, which is the line bundle that gives you that embedding into projective space.
Okay.
So there's sort of a lot of stuff here which, you know, I tend to kind of secretly translate into complex algebraic projective algebraic geometry in my head, and I will make some comments about that, which will probably be very illuminating for a few people and be very confusing for some others.
Okay, maybe I'll ask again about it in some other time or office hours or something like that. So.
But yeah, I mean, one way to think about this is there's this whole, I think the term is Churn Theory about, you know, taking a class in H2 and writing it as the curvature of a connection on a line bundle, and there's an integrality condition. And maybe one extra thing I will say is, you know, in like the very first class, I was talking about classical mechanics, and one of the students had asked, oh, what about quantum mechanics? Right? And so that condition about your Kähler form being integral, that's a kind of quantization condition. So the conditions like that show up when you want to say, oh, I had a classical, you know, physical system coming from a symplectic manifold. Now I want to turn it into a quantum one. You actually want integrality conditions like that for it to work. So, you know, right? Being integral is a quantum thing. But it makes something more discrete. All right. Any other questions? So one of the kind of really cool things about Kähler manifolds is you can actually describe all of this structure. You have to think of the complex structures fixed at first, but the metric and the symplectic form can all be sort of contained in one single smooth function. So consider a smooth function from M to R, and this has this horrible name, strictly plurisubharmonic, which I will always shorten as SPSH, SPSH. If when I take the second derivative with respect to zi, so the complex variables and then their complex conjugates, dz, j bar, I get a matrix, and that matrix has to be positive definite. And I'll just mention it's automatic that it's Hermitian because of the commutation of mixed partials. So, but it's an extra condition on this function that some functions will satisfy and some won't, that it's positive definite. And in fact, if you are already on a complex manifold and you have a function which is, yeah, well, right, I'm using the complex structure and defining SPSH. So the function is strictly pluri-subharmonic if and only if, when I take my function, I do d bar to it first. So that gives me a 0, 1 form. And then I do del to it, and I get a 1, 1 form if I over 2 times that is a Kähler form. So if I wanted the metric instead of the symplectic form, right, then I would be looking at just this matrix. So I have to multiply by I to get the actual Kähler symplectic form. So note here, so first I want to show you that if I start with a strictly pluri-subharmonic function, then the resulting form is Kähler. Well, how do I check that? Well, I need to check that it's closed. That's roughly obvious. The only slightly tricky part about it is I have to use this relation that del del bar is equal to minus del bar del. So this was a consequence of the fact that del plus del bar squared equals 0. So this is one of the conditions that was equivalent to being a complex manifold. So when I take d of omega, well, I can break that up into del times omega and del bar times omega. Del bar squared is 0, so that's okay. I think I wrote the wrong thing. No, I did write the right thing here. Right. And then del bar times omega, I have to rewrite this guy as minus I over 2 del bar del rho. So when I write it that way, it's clear that del bar times it is 0. So it's closed, that's good. And on the other hand, if I kind of write out explicitly what's happening, right, these mixed partials, derivative with respect to zi and zj bar, are exactly the coefficients of dzi wedge dzj bar. And we had already seen before that being Kähler was basically equivalent to this guy to being closed and to this guy being Hermitian positive definite. So being strictly pluri-subharmonic implies that this guy is Kähler. And similarly, if omega is Kähler, then, well, these mixed partials exactly give me the matrix that had to be Hermitian positive definite in order to be Kähler. So my original function was strictly pluri-subharmonic. Sorry, I'm just going to have to keep saying that, I know. They really should have come up with a better name. All right, so let's look at an example. So on Cn, you can let rho just be the square of the usual norm on Cn. So if I do that, well, del bar of this guy, right? I can write this as the sum of zi times zi bar. So when I differentiate with respect to, I should make sure it's clear this isn't a del, it's a usual d. When I apply del bar to it, right, I have to take the derivative of this function with respect to zi bar, which is zi, and then multiply that by dzi bar. All right, so then I take del of that guy. Now I'm applying del to each of the zi's, and I just get dzi. I wedge that together with the dzi bar. And then if you write out explicitly what dzi bar wedge dzi is, then you get exactly that. I over 2 times that is the usual symplectic form, dxi wedge dyi bar. Dy, there's no bar. Sorry. And those i's exactly account for the fact that this guy actually isn't a symplectic form on the nose. It has a weird factor of I in it, coming from the I times yi. All right, so this gets us that the metric is just the usual one coming from the obvious L2 norm on Cn, and it's the standard symplectic structure and the standard complex structure. So kind of the obvious compatible triple comes from this relatively obvious function. All right, and this hopefully gives you kind of a little bit of a feel for what's going on. So point is somehow being strictly plurisubharmonic basically means you're kind of not too far away from having this form. Obviously, you're not going to have that structure on the nose, but you look a bit like this guy in some coordinates, you know, with some modifications. All right. Now, unfortunately, usually a Kähler form is not going to have this structure, but it will locally. Let me state this theorem and then we'll take a short break. So it's not true that every Kähler manifold has a global function that satisfies this, but at any point, there's always a neighborhood where you can pick what's called a Kähler potential. Should have written this. Row is called Kähler potential. So for any point, if you have a Kähler form on a manifold and you choose a point, there's always a neighborhood of that point where your Kähler form actually is at this point. And I'm just going to note, you essentially can never do this globally on a compact manifold because your symplectic form has to have a non-trivial class in H2. And so you're never going to be able to write it as del of something. All right, now let me pause. Does anybody have questions before we take a short break? Okay, I will step out for a moment, get some water, and I'll see if people have questions when I get back. All right, did anybody think of any questions while I was gone? All right, then I guess we'll keep talking. So let me just kind of quickly mention the proof for this. You end up having to use the Poincaré lemma twice, and one of those is actually the del bar version of the Poincaré lemma. So first of all, by the usual Poincaré lemma, we can restrict to a small enough neighborhood such that omega is the usual exterior differential of some one form. And I'll note here, right, you're never going to be able to do this globally on a compact symplectic manifold. The symplectic form is never exact in that case. So you sort of see already, we've given up on doing this globally. We're only going to do it in a small neighborhood. we can write this guy alpha as the sum of its, I shouldn't say holomorphic. It's 1, 0 part and it's 0, 1 part. So again, this is not whether it's holomorphic or not, which is a stricter condition, but whether it's complex linear or complex antilinear. All right. So you can check the fact that D of this is a 1, 1 form, tells you that del bar kills the 0, 1 part of alpha. So using del bar Poincare lemma now, so again, we might have to shrink even more. There's a del bar version of the Poincare lemma that says on a sort of small enough neighborhood, any exact del bar closed form is del bar exact, unless it's already holomorphic. All right, so this 0, 1 component can be written as del bar of some function. And one of the things you have to kind of keep track of carefully here is alpha was real valued, but when I split it into its complex linear and complex antilinear parts, I started using complex coefficients. So alpha is complex valued, f is going to be complex valued. And the existence of that requires a del bar version of Poincare lemma, which is true, but which we're definitely not going to prove. And we're again going to use this fact about how del bar works. That if I look at del bar of f, that's some 2 form, in fact, a 1, 1 form, and which I'll call beta. And if I take its complex conjugate, I get del bar del f bar, which I can swap the del and del bar, but at the cost of adding a minus sign. So that's minus del bar f bar. All right. So I can write omega as del of this 0, 1 part plus del bar times the 1, 0 part of alpha. That's actually beta plus beta bar. I can write omega as 2 times the real part of this guy beta. That's the same as del bar times f minus f bar. So actually the function I need up to multiplication by a scalar is the imaginary part of f. Again, this is where I kind of have to think carefully about what's real valued and what's complex valued. F is complex valued, but its imaginary part is sort of the function that makes all of this work. And why is it imaginary part instead of real part? It's because of this silly minus sign that shows up. Not silly, it's pretty important. Kind of forces us to stick in all these factors of I. All right, so good. Kähler potentials exist. One thing that's nice about this is it makes it sort of clear that complex submanifolds of Kähler manifolds are Kähler, because you just restrict the Kähler potential. And this actually has the effect of just you restrict the symplectic form, you restrict the metric, and everything that was Kähler before, the sort of Kählerness descends to this complex submanifold. So this is a really good way of cooking up interesting Kähler manifolds. You have a few Kähler structures you know well. As I mentioned, there's the one on Cn, and then there's the one on Cpn. And so closed submanifolds of Cn or Cpn, which are complex, inherit Kähler structures. Right. So, again, as I said, I often kind of end up translating this stuff in my head into algebraic geometry. So one important subclass of smooth complex submanifolds of Cn are smooth affine varieties over C. So those always have Kähler structures. In general, closed complex, and when I say closed, I don't mean compact, I just mean closed as a subset of closed submanifolds of Cn are what are called Stein manifolds. So these are kind of the analytic version of smooth affine varieties. These sort of play a pretty important role in, for example, symplectic geometry. So similarly, you'll show on the homework that CPN is Kähler. And so any smooth projective variety over C is Kähler. I'll just note here, there are lots of Stein manifolds that aren't affine varieties that you can write as like the zero sets of analytic functions that aren't polynomials. But there's this theorem with the slightly ridiculous name of Gaga. That is really what everyone calls it. That's an acronym for Géométrie algébrique, Géométrie analytique, which is a very famous paper of Serre's on this topic. Any closed submanifold, complex submanifold of CPN is actually a projective variety. It's defined by polynomials. So for example, that includes all Riemann surfaces. And those are always Kähler. So somehow, like, you might think that there should be like weird analytic subvarieties of CPN, but some sort of magic forces that to not happen. And I mean, it's actually not a very hard theorem, but maybe I won't get into it. It's sort of something you have to know a little bit about algebraic geometry to understand. All right, so this is kind of a big source of examples. And particularly, this is a big, interesting source of symplectic manifolds we didn't know about before, right? Up until this point, there's nothing obvious about the fact that a smooth projective variety over the complex numbers has to have a symplectic structure. But now we know it does because it has a Kähler structure, and that includes a symplectic form as part of it. And this is actually a very interesting source of symplectic manifolds. And I just sort of mentioned here, this point that Matthew was asking about earlier. When I have a submanifold of CPN, well, that has an induced Kähler structure. And actually, at least the kind of usual way of choosing a Kähler structure on CPN, the Kähler class is exactly the hyperplane class inside CPN, if you know the cohomology and homology of CPN. Since the second cohomology is one-dimensional, you can always scale the thing to be integral. And somehow if you're kind of used to thinking about like divisors in algebraic geometry, right, what ends up happening is a projective embedding of some algebraic variety inside complex projective space corresponds to a divisor in that variety that comes from intersecting with a hyperplane in CPN. So you get a codimension 2, complex codimension 1, real codimension 2 subvariety. And that should be Poincare dual to the cohomology class of the Kähler form, right? So that, so I have CPN. Inside there's a copy of CPN minus 1, which you can think of as the closure of any hyperplane. If I have X inside here, well, then I have X intersect CP1, CPN minus 1. And I can think of this guy as being a 2n minus 2 dimensional homology. Oh, whoops, I shouldn't make that cohomology, I should make that homology. I can. 2n minus 2. By Poincare duality, that's the same as H2, and that corresponds to the Kähler class, for the Kähler structure restricted from CPN. And then there are other Kähler structures that just don't come that way, that you can get by like averaging ones coming from different embeddings in CPN, for example. All right. Any questions? All right, so we now have sort of a lot of possibilities. I essentially had this kind of chart before, but let me draw this in a slightly different way. We can have kind of bubbles of, well, there are Kähler manifolds, and then symplectic manifolds include Kähler manifolds inside them, as do complex manifolds, and then almost complex manifolds include this whole picture. And you can ask kind of what regions in this Venn diagram are non-empty. So are there almost complex manifolds that aren't complex or symplectic? Are there symplectic manifolds that aren't also complex manifolds that aren't also symplectic? One interesting one we'll get to is, can you have a manifold which both has a symplectic structure and a complex structure, but not in a way such that they play together and make a Kähler structure? And of course, answering questions like this can be hard, because if there is a Kähler structure, well, you just write it down. You say, look, here it is. Here's the Kähler metric, right? But if you think there isn't one, how do you obstruct it? So we've had a really good condition about this for finding symplectic manifolds, right? If you have a symplectic manifold, the cohomology class of the symplectic form will be non-trivial. And in fact, the cohomology class of all of its wedge powers will be non-trivial, because you have to get a top form when you take the top power of it. So you have to have all of the even cohomology groups between 0 and the dimension of your manifold are all non-zero. So this is a really strong obstruction to being symplectic. And so, for example, S6 we know is not symplectic, but we do know is almost complex, right? And it's in fact an open question whether it's complex or not, because we don't have good enough obstructions to being complex. So being Kähler actually has an even stronger effect on the topology of group variety. And we'll see how much I have time to discuss this. I wrote out quite a bit here, but actually a class in complex geometry, so we'll see how deep I get into this. The theorem that sort of gives you a really powerful control on the topology of a Kähler variety is this sort of circle of theorems in what's called Hodge theory. One of the most basic ones being, on this side we have Dolbeau cohomology. I swear I can spell this name. Dolbeau, great. So on one side I have Dolbeau cohomology, and on the other side I have usual de Rham cohomology. And these things are, for a Kähler manifold, effectively the same. So the de Rham cohomology in some degree is just equal to the direct sum of the Dolbeau cohomologies, where the pair of indices sum to K. And I'll say more about this later. The other kind of key thing, and all of this you need being Kähler for, is that if I swap the two indices, I'll get an isomorphic vector space. And so in particular, one of the key consequences of this is odd Betti numbers have to be even. We'll sort of go into this in more detail, but let me say a little bit about what you need in order to do this. So in order to do Hodge theory, the first thing you need what's called a Hodge star operator. So for any vector space, I have a non-degenerate pairing from the kth wedge power to the n minus kth wedge power to the top wedge power, which is one dimensional. And so if I choose an isomorphism of this guy to R, I will get a pairing between these two spaces. And so I get an isomorphism between wedge to the k of v and wedge to the n minus k of v dual. And the kind of geometric way to think about this is the most important wedges, kth wedges, are the volume forms on k-dimensional subspaces. And I'm going to send that to the volume form on the n minus kth annihilating subspace in V dual. And those volume forms are normalized because I have fixed a volume form because I fixed a volume form. Right? If I also choose an inner product, then V is isomorphic to V dual. And so I get an isomorphism from the kth wedge power to the n minus kth wedge power. And you'll often see this kind of explicitly written out in coordinates as I take the wedge of k basis vectors in an orthonormal basis, and that gets sent to the wedge of all the other basis vectors, which span the perp. And then you just have to be careful about signs to get all the orientation stuff right. I think it would just be a distraction to try to write that out again. Either you kind of know about Hodge star already, or it wouldn't really mean anything to you. So in an oriented Riemannian manifold, in particular on a Kähler one, you get this star operator that relates k forms to n minus k forms. And on a Kähler manifold, that sort of behaves well with respect to this decomposition into PQ forms. Using the star operator, we define a Laplacian. Often you'll see people write this operation of star, take exterior derivative, and star again as d superscript star, or sometimes a d with a different style. So this is d star d plus d star. And sort of the key thing about Hodge theory is having this Laplacian, looking at its properties, and looking at things which are harmonic. So we call a K form harmonic if it's killed by this Laplacian. If Laplacian is 0. All right. So kind of the key thing that makes Hodge theory go is that if I have a compact Kähler manifold, then any class in Duran cohomology or Gaubois cohomology has a unique harmonic representative. And the kind of intuition is you look in that cohomology class and you look for something that minimizes the norm. So this having a volume form and the star operator gives me an inner product on the space of K forms, which is, well, I star one of my forms and then I wedge them together and I integrate that over the manifold. So if I take something, star it, and then wedge it together with its own star, I get a norm on the space of K forms. And if you look through kind of what you need to be somehow blanking on the critical point of this norm, it's exactly that you have to be harmonic. So if you have a minimum in your cohomology class of this norm, it should be a harmonic form. But there's sort of serious analysis required to actually show that such a thing exists. So it's sort of a pretty standard, straightforward thing that there can only be one harmonic representative, but actually knowing that there is one that's a smooth form that involves sort of real work and actual analysis. The version for de Rham cohomology doesn't require any of this fancy stuff. It holds for any Riemannian manifold. The key thing that you need being Kähler for is to make sure that being harmonic plays well with this decomposition into KL forms. Or, sorry, LM. I think I changed my mind a few times about what these indices should be. But the key point is, if you are Kähler, then if you start with a harmonic form, it's projections to the K, let's say PQ forms. I think at some point I was reading enough stuff that used PQ that I just switched over. Your projection to PQ forms will also be harmonic. So that's kind of where being Kähler is kind of key. So in that case, that means that the space of harmonic K forms can just be written as the direct sum of all harmonic PQ forms where P plus Q is equal to K. Right? Every harmonic K form, you can look at its projections to the space as PQ. Because the metric is Kähler, all of those will be harmonic. And I've got the decomposition I need. So the space of harmonic K forms, that's the same as the kth de Rham cohomology. And the space of harmonic PQ forms, that's the same as the PQ Dolbeault cohomology. And so just this basic fact that the harmonic forms break into harmonic PQ forms gives me this isomorphism of de Rham cohomology and Dolbeault cohomology. In general, sort of the Dolbeault cohomology is bigger. So if you have some random, complex manifold with a metric that isn't Kähler, then what you would expect is that there are sort of Dolbeault classes that somehow you can't turn into a de Rham class, right? So there's no reason that a representative of a Dolbeault cohomology class, the Dolbeault cohomology class has to have a representative that's closed for the whole exterior differential. So, sort of lots of bad things can happen if you're not in this compact Kähler situation. Right, so one important example here is, if I start with a harmonic PQ, complex conjugate is a harmonic QP form. But if I were just looking at Dolbeault cohomology presented the usual way, right, then I have something exact, del bar exact. But if I take its complex conjugate, there's no reason that that should be del bar exact, right? So, that's only going to happen if it's also true that del of C is 0. That's only going to be true if dxc is equal to 0. So for example, it's worth thinking about, like, just to give you a simple example, C star, right? The 1,0 Dolbeault cohomology is all of the holomorphic functions, all of the functions that are killed by del bar, and the 0,1 Dolbeault cohomology is trivial. Because every 0,1 form is del bar of some function. The example that kind of usually comes up in discussions of this stuff is if I look at Cn, I remove 0, and then I mod out by identifying x with 2 times x. then I get actually a manifold which is homeomorphic to S1 times S2n minus 1. Basically, I get a circle that comes from the radial direction, and then I get an S2n minus 1 from the unit sphere inside Cn. And this is not Kähler. And I would want to check again I think in this case it's that H10 is 0 and H01 is one-dimensional, but I'm not absolutely sure about that. It could be the other way around. I don't have the source I pulled this from in front of me. But you get this kind of asymmetric picture. And exactly the problem is there's no reason that a Dolbeau cohomology class should have a representative which is exact. And there's no reason that Dolbeau cohomology should sort of play well with taking complex conjugate. So you need these harmonic representatives to make sure that's true. All right, so this tells you that the cohomology of a Kähler manifold has a really special structure. So you have these things that are called Hodge numbers, which are the dimensions of the Dolbeau cohomology. And you'll usually see these represented in what's called the Hodge diamond, where you write them in this form with the first index increasing as you go northwest, and the second index increasing as you go northeast. So, whoops, I shouldn't write a 1 there, I should write 0. H0, 0, and then going up through Hn0, H0n, Hn. And what you get here are the Betty numbers, just summing across rows. So top Betty number is Hn, bottom Betty number is H0, 0. And then if you have one in the middle, it's a big sum of these guys. All right. So this diamond, it has some really nice properties. It's this property about complex conjugation means if I reflect in a vertical axis, the diamond stays the same. Now, I said here that I can reflect in a horizontal axis because of Poincare duality. That's a little bit of a lie. What Poincare duality actually lets me do is 180-degree rotation, but then combining that with a vertical reflection, I get a horizontal reflection. So it's symmetric under both of these reflections. It's not symmetric under a 90-degree rotation. Should emphasize that. And this has this very useful property that it means that an odd Betty number, right? If I have an odd row here, then I have, for example, H10, H01, and the sum across the row breaks up into two equal pieces, the stuff on the left side and the stuff on the right side. So I can write this Betty number as 2 times the stuff on the left side, 2 times the sum of these Hodge numbers where P is bigger than Q. It's also 2 times the sum of the Hodge numbers where Q is bigger than P. And this is a really useful obstruction to having a Kähler metric. So if you have an odd index Betty number, which is odd, then you don't have a Kähler metric. There's another kind of nice property with this, which This unfortunately isn't mentioned in Canis de Silva, but it's one I like very much, and one that's actually pretty important for combinatorics, which is what's called hard Lefschetz. So let me say this in words. Here it is in formulas. It's as you go up toward this middle line of the diamond, you increase. You're weakly increasing as you go up. And then by symmetry, you weakly increase as you go down toward the middle as well. So as I look at a column, it's unimodal. I go up for a while and then down for a while. And it kind of has to be that way because of the symmetry. And despite the name, this isn't actually a very hard theorem. Again, because the symplectic form is closed. So I'm using all over the place here that I have a Kähler manifold. Wedging with the symplectic form gives me a map from the PQ cohomology into the P plus 1, Q plus 1. So wedging with the symplectic form preserves being harmonic. And so I get these maps, and then I have a map going back the other way, which is star first, wedge with the symplectic form a bunch of times, and then star again, right? That will take me back in the other direction. And I can show that composing those gives me an isomorphism from HPQ to itself. So there are various sort of other ways of arguing this. One that maybe I like better, but which requires a bit more background, is you can actually use wedging with the symplectic form and this dual starred version of it to generate a representation of SL2, where what degree of the cohomology you're in tells you your weight as an SL2 representation. And then you get to say, oh, SL2 representations exactly have the structure where they come in chains. And this middle cohomology degree is the weight 0 part of the SL2 representation. So that's kind of maybe a more satisfying answer for why this is true, but it requires you to know about the representation theory of SL2. And I think you don't really need it. Somehow the sort of important point here is if you have a, between these two groups, wedging with the symplectic form always sort of sends non-zero forms to non-zero forms. It's actually pretty, if you really think about the linear algebra, it's pretty simple. Okay, so let's do a few examples. The most obvious example that's not that interesting is if I have a Riemann surface of G is G fourth cohomology and the second cohomology are one-dimensional. And the middle cohomology is 2G dimensional. So the two Hodge numbers are both G. And you see this manifestation of odd Betti numbers are even. If you have a Riemann surface that's compact, its first Betti number is always even. It's 2 times the genus. On the other hand, if I have CPN, let me just kind of draw what this diamond is. Well, I just have all ones down the diagonal, right? So I know that my symplectic form actually generated the wedge powers of the symplectic form span the cohomology of CPN. If you know what the cohomology of CPN looks like, it's a polynomial ring mod the relation that if you go too high, you get 0. So, well, the symplectic form has to be a 1-1 form. So all of its wedge powers are 2-2 forms, 3-3 forms, 4-4 forms, and everything sits along this diagonal. So I was making sort of this comment earlier about the fact that, as a geometric representation theorist, somehow I think about a relatively odd set of varieties. And one of the things that is true is way more often than usual, it involves varieties that have the structure of everything just sits on this middle column in the Hodge diamond. This is what's called a pure Hodge structure. Well, not just pure, but no, there's some other fancy name for it. But it's a very boring Hodge structure. But many varieties you might have heard of have this structure. So, if you know about projective varieties, maybe the second one that would come to your head is Grasmanians. Grasmanians also have this structure of everything being in the middle. So do toric varieties. And one way to think about this is if you have a homology class that comes from a complex submanifold, its Poincare dual will always sit on the diagonal. On this middle column in the Hodge diamond. So if you have a complex variety where all of your homology is generated by complex subvarieties, your cohomology, everything is going to sit on this middle column in the Hodge diamond. And again, like I quite often think about varieties that have that property. That's actually a very rare property if you think about like the whole world of algebraic varieties, right? For example, if you have any odd Betty numbers, well, you have homology classes that can't come from something complex, right? So the kind of example to think about is if you have this Riemann surface, well, you need to have one-dimensional submanifolds generating elements of your homology, and thus can't be complex. So any higher genus Riemann surface breaks this. Okay, yeah. Right. So this is it's very atypical behavior, but it's a very important kind of behavior that you see in some very important classes of varieties. And just to give you a sense of, they don't all have this totally simple structure. One variety I'm sure we'll talk a little bit about later is I look inside CP4 and I look at a generic degree 5 polynomial on CP4 and consider it 0. So this is a hypersurface in CP4. It's real 6-dimensional complex 3-dimensional. If I pick a generic polynomial, the Hodge diamond has this kind of strange structure of, well, it's all ones down this main middle column. That looks pretty reasonable. I have zeros here, zeros here. I have ones out at the far edges. Those ones, these are actually manifestations of the fact that this guy is Calabi-Yau, which we'll discuss a little bit later. For now, Calabi-Yau means that I have a 1 at this outer edge of the Hodge diamond, the very far left column that only has 1 entry in it. And then there's this crazy entry, which is 101. And like there is a good explanation for where this 101 comes from, some combinatorics behind it, but it still looks pretty surprising to me. There's some numerical calculation you can do where you can see that this guy has Euler character, excuse me, Euler characteristic minus 200. And so you're forced to have some very big cohomology group somewhere. And I'll just mention, one thing I had kind of put as a topic I'd like to say a little bit about at the end of the course, in which many people who filled out the Getting to Know You had mentioned, was mirror symmetry. Well, so what mirror symmetry actually refers to is you can have one Kähler manifold with one Hodge diamond, and then you can reflect in one of the lines you're not allowed to reflect in, which effectively is the same as a 90-degree rotation, but it's called mirror symmetry because you can be reflecting through one of these lines instead of a vertical or horizontal one. And well, you won't get the same Hodge diamond back, but you'll get the Hodge diamond of some other Kähler manifold, which in this case is another projective variety, and that's supposed to be its mirror pair. In this 3-dimensional case, or complex threefold case, so it's actually 6-dimensional, this H11, that's where the Kähler class lives. So a class in there controls the symplectic structure. And on the other hand, you can think of a class in here as controlling a deformation of complex structure, right? Choosing all the kind of different ways of choosing these polynomials, right? I said pick a generic one. Well, there are a lot of choices there. And mirror symmetry is supposed to sort of swap deforming the Kähler structure with deforming the complex structure. And that sort of manifests in this reflection of the Hodge diamond. All right, so that's something we'll discuss in some more detail later. This is just kind of the very first hint of it. And as I said, this condition on Betty numbers can be used to show that there are manifolds out there that aren't Kähler. And in fact, there's a manifold that has a symplectic structure and a complex structure, but not a Kähler structure. So even though there's a complex structure and a symplectic structure, you can't make them compatible such that they become Kähler. And it involves a particular quotient of Cn by a discrete group whose Betty number is 3. First Betty number is 3. We have an odd Betty number that's odd, no Kähler structure. All right, and I'll just refer you to Canis de Silva for kind of all the examples of all the other things that can happen. Basically, any kind of combination of these structures existing or not existing that you can imagine, it happens. This is one of these situations of sort of Murphy's law of if you don't know a theorem that tells you something can't happen, probably it does. Yeah, I'm out of time, so I'll refer you to Canis de Silva and open the floor up for questions.